Hello and welcome to this lesson on chemical cells. In today's lesson, we will firstly understand the basic functioning of chemical cells. We will then go on to identify the factors that determine the voltage output of a chemical cell. Finally, we will look at the distinction between single cells and batteries. Let's get started. So far, we've explored the topic of energy changes in chemical reactions. Specifically, we have looked at how energy is absorbed or released during chemical reactions. Building on this foundation, today's lesson will advance our chemical understanding by delving into how chemical cells work. This will deepen our appreciation of the interplay between chemistry and electricity, highlighting how chemical reactions can be harnessed to produce electrical power. Chemical cells convert chemical energy into electrical energy through chemical reactions. They are foundational to many everyday technologies, providing the power needed for everything from clocks and remote controls to electric cars and renewable energy storage. A chemical cell is made of two electrodes immersed in an electrolyte. The electrodes are each connected to a voltmeter to complete the circuit. Let's examine each component in more detail. Electrodes are made of two metals of different reactivities, typically zinc and copper. The more reactive electrode loses electrons more easily. So in the case of zinc and copper, this would be zinc as it is more reactive. The zinc electrode thus acts as the anode, where oxidation or loss of electrons occurs. The other is the cathode, where reduction or gain of electrons happens. We will take a closer look at electrodes in the next lesson. The electrolyte is the substance in which the electrodes are immersed. It contains ions that can move and carry electric charge between the electrodes. This solution allows ions to move between the electrodes, facilitating the chemical reactions, oxidation, and reduction at the electrodes that release electrical energy by creating an electric potential or voltage between the two electrodes. It causes the electrons to flow from the anode to the cathode through the external circuit, meaning current is generated, which generates voltage measured with the voltmeter. The choice of electrolyte is crucial because it must facilitate the movement of ions without reacting too much with the electrodes, which would reduce the cell's efficiency. The voltmeter is an instrument connected to the electrodes to measure the voltage or electric potential difference between them. This voltage indicates the cell's ability to generate electric current. By reading the voltmeter, we can gauge the cell's power output. Connecting the electrodes to the voltmeter completes the electric circuit, allowing electrons to flow from the anode to the cathode through an external circuit. This flow of electrons is what we harness as electric power. In a simple zinc-copper cell, zinc at the anode loses electrons and becomes zinc 2+ ions. The electrons lost from the zinc anode flow to the copper cathode. Copper at the cathode gains electrons and deposits as copper metal. These reactions create a flow of electrons from the anode to the cathode through an external circuit, converting the stored chemical energy into electrical energy. Several factors influence the voltage output of a chemical cell. Different combinations of materials for the anode and cathode result in different voltage outputs. For example, a zinc-copper cell typically produces about 1.1 volts. The nature of the electrolyte, for example, acidic, basic, or salt solutions, and its concentration also impacts the efficiency and voltage of the cell. We will expand on these ideas in subsequent lessons. But suppose we have one type of cell and we can't change the inner structures, but we want to generate more voltage. We can do so by connecting cells end-to-end or in series. When we connect cells in series, we link the positive terminal of one cell to the negative terminal of the next cell. By doing this, we add together the voltages of each individual cell. For example, consider two cells which each produce 1.5 volts of electricity. When we connect these two cells in series, we get a total voltage of 3 volts, which is simply the sum of 1.5 volts and 1.5 volts. If we add a third cell, we get a total voltage of 4.5 volts, as we add 1.5 3 times. We call such an arrangement a battery. To be precise, while a single cell consists of just one set of electrodes and one electrolyte solution and typically produces a limited voltage and capacity, a battery is a collection of multiple cells connected in series which combine to produce a larger total voltage. We will examine batteries in even further detail in subsequent lessons. Before we conclude, let's consider the history of chemical cells as an extension task. The development of chemical cells, or batteries, began with Alessandro Volta's invention of the voltaic pile in 1800. The voltaic pile was the first true battery, consisting of alternating discs of zinc and copper, separated by pieces of cloth soaked in salt water. This ingenious setup provided a steady flow of electrical current and paved the way for modern electrochemistry. Volta's work revolutionized how we generate and use electricity, leading to the development of all the batteries we rely on today, from powering our smartphones to running electric cars. In today's lesson, we delved into the functioning of chemical cells, which convert chemical energy into electrical energy through chemical reactions. We examined the structure of a chemical cell, focusing on the roles of the anode and cathode, as well as the electrolyte solution. We learned that the anode undergoes oxidation, losing electrons, while the cathode undergoes reduction, gaining electrons. This electron flow creates a potential difference, driving an electric current through an external circuit. We also explored how the voltage output of a chemical cell is influenced by factors such as the materials used for the electrodes, the nature of the electrolyte solution, and the specific chemical reactions taking place. Finally, we distinguished between single cells and batteries. Understanding these concepts enhances our ability to harness chemical reactions for practical electrical energy production, paving the way for innovations in rechargeable batteries and fuel cells.